In this video, I'm going to teach you how to analyze velocity time graphs. We're going to be looking at the same graphs generated from the PHET simulation called the moving man. We're also going to consider the same four questions. What is the significance of the slope? What is the significance of the area under the graph or curve? What is happening if the graph crosses the horizontal axis? And what does it mean if the graph is curving? So let's go ahead and look at this portion of the velocity time graph and answer the question, what is the significance of the slope? Let's look at this region between 8 seconds and 10.5 seconds. So we're going to calculate the slope using the rise over the run, or that ratio of the change in the vertical axis over the change in the horizontal axis, which is velocity over time. I've indicated those points roughly on the graph, and we're going to now put in our values to calculate the slope, paying attention to the signage, and we get that the slope of this region is a positive 2.0 meters per second per second. So the slope of the velocity time graph is indeed the acceleration. And recall that acceleration, by definition, that vector quantity, is the change in velocity over the change in time, which is exactly what we're calculating when we find the slope from a velocity as a function of time graph. As yet another reminder, in AP Physics 1, we are dealing only with uniformly accelerated motion, commonly referred to as UAM. Also, when we look at the units, which is always important, we have meters per second multiplied by the inverse of 1 second, which gives us the base SI units for acceleration of meters per second, or meters per second squared. Now let's look at this region of the graph. Pause the video, see if you can calculate the slope. And remember, we're looking for an estimation. So when we plug in values for the rise over run in this scenario, we end up, again, pay attention to signage for vector quantities of a negative 1 meter per second being our final velocity minus our initial velocity, which was positive 5 meters per second, divided by the change in time, which in this case was 12 seconds minus 10.5 seconds as read from the graph. That's going to give us an acceleration of negative 4.0 meters per second for this second region on the graph. Now, let's move on and talk about the significance of the area under the graph or curve. For velocity time graphs, this area is the displacement or change in position. So calculate from this graph the displacement for the moving man in the first 6 seconds of motion. I'm going to teach you how to use this graph to find the displacement or change in position. I'm also going to teach you how to use this graph if you were asked to calculate, say, the final position given a graph. That's coming up here in a couple minutes. So let's calculate the displacement of the moving man. When we translate this into the physics, this question is saying, find the area under, and it's under quotations because that is relative. Here is the area under that portion of the graph, and here is the area under the second portion of the graph. So it's above that portion of the graph. All right, so let's look at these two areas. In this course, you're finding the area of rectangles, squares, and triangles. If any region is curving, and I'll expound on this in a later video, you can still estimate the area under using triangles, squares, and rectangles, because to truly find the area under a curve, you would need to use integrals and calculus. In AP Physics 1, you are good estimating that area. Okay, so here I have two rectangles in this time, and I'm going to take the first area, which is a 2.5 meters per second that occurred for 2 seconds. So base times height, and I'm going to add this other area here, but I must pay attention to signage. So that was a negative 5 meters per second multiplied by, on the horizontal axis, the base, which is 2 seconds. So base times height plus base times height. I have these two areas of these rectangles, and I'm now going to add them together. That is going to give me a value of negative 5.0 meters. And that is the change in position or displacement for the moving man. Of course, if we continue, as I've always said, to look at units, meters per second, multiplied by seconds, where these would cancel out and we are left with meters, the base SI unit for distance, for position, for displacement. All right, so now let's go ahead and look back at our position time graph. So we calculated finding the area under the displacement to be negative 5.0 meters, or 5 meters to the left. This is looking back at our position as a function of time graph, and indeed, at time equals 6 seconds, we see the moving man's position is at negative 5 meters. So that is his displacement between time 0 seconds and time 6 seconds, which is what we calculated for this particular problem. Now, let's look at another example, and I alluded to this earlier. In this problem, let's calculate the final position of the moving man after 10.5 seconds of motion. So we're still using the area under this graph. But in this instance, we're using it not to find the overall change in position or displacement, but to find the moving man's final position. Now, we just got done calculating the moving man's displacement for the first 6 seconds of motion, and hopefully it's evident between 6 and 8 seconds, the moving man is not moving at all. His velocity is 0 meters per second. And so for this next duration of time, we have ourselves a nice little triangle here between t equals 8 and t equals roughly 10.5 seconds. That's an estimation there, and it's good enough for what we're trying to calculate. So we're going to do 1/2 base times height, where our base are the seconds at 2.5 seconds. The height is the velocity, which is a positive 5 meters per second, and 1/2 that gives us a value of 6.25 meters. So this quantity on the left side of the equation is 6.25 meters. Over here, we're taking the fact that we already know x naught. We're defining, we know that initial position of the moving man right here at 8 seconds is negative 5 meters. So then we're going to take negative 5 meters and we're going to plug it in here. Now pay attention, you have a double negative here, which gives you a positive. But then to solve this equation for x final right here, you need to subtract that positive value from both sides. So again, we have a double negative. We're subtracting a negative 5 meters. That gives us positive 5 meters. But then to solve the equation, we're subtracting 5 meters from both sides. So 6.25 meters minus 5 meters gives us our final position for the moving man at a positive 1.25 meters, or 1.25 meters to the right. Now let's go ahead and revisit the position as a function of time graph, and let's look at where this moving man was at 10.5 seconds. You can see the arrow is right around 1.25 meters. So this calculation makes sense. Our next question, what is happening when the graph crosses the horizontal axis? Okay, let's look at that. So the object has stopped, and when it crosses the horizontal, it has changed directions. As it is along the horizontal axis, it has stopped. That's one of those areas when you're trying to read and analyze more complex motion time graphs. This is something I urge students to pause and consider. If it's crossing the horizontal axis and you are looking at a velocity as a function of time graph, then at that instant, the object has stopped. And if it moves beyond, it is moving backwards. So if it crosses the horizontal, then the object is moving in the negative direction. So looking at this graph here, it is velocity equals 0. Velocity is some negative quantity here, and we already know that the velocity is negative 5 meters per second. And then here we have velocity equals 0, and of course here the velocity is positive. So it's important to look at what is happening in these graphs when they cross the horizontal axis. Now, my final question is, what does it mean if the graph is curving? Well, we don't have that in a simulation, so I'll go ahead and sketch that in. Whoa, what's happening here if the graph curves and we're looking at velocity as a function of time? Foremost, remember, again, AP Physics 1, we're considering constant acceleration. We're looking at uniformly accelerated motion. But you have enough knowledge to be able to interpret this, and that's important to me. This is simply showing that the acceleration is changing. It's not uniform. It's not constant. It's increasing over time. And I feel that it's important for my students to at least be able to look at this and say, yes, that is realistic. This does occur. Acceleration can increase over time. That rate can increase over time in real life. So in this video, we've continued to look at a number of learning objectives dealing with motion and analyzing motion graphically, and I'll see you guys in class.